All right. So good evening. My name is Eyal de Lara, and I have the pleasure of serving as the chair of the Department of Computer Science, and it's my pleasure to welcome you all tonight. So it's a pleasure to welcome you all, to those of you that are joining us here in person, as well as those that are watching online. This is our very first ever talk that is part of the Kelly Gottlieb Distinguished Series that happens in the evening, so we're making history here. So the Kelly Gottlieb Distinguished Lecture Series is really the premier series that the Department of Computer Science runs. It's in honor of our inaugural chair, Professor Kelly Gottlieb, who pushed U of T to the forefront of computer science in Canada and truly, really in the world. And he's one person who's really largely credited with being responsible for leading Canada into the modern age of computing. For more than a decade, this series has welcomed top minds to the Department of Computer Science and to the university to discuss the research in the field. As some of you may know, this academic year, we're actually celebrating the 60-year anniversary of the founding of the Computer Science Department here at U of T. Over the past 6 decades, the department has made tremendous strides in strengthening and advancing the field of computer science in Canada, as well as the world. This year provides an opportunity to celebrate that impact, as well as the promise that the future holds. And I'm thrilled to have you here join us in person to take part of this celebration. This year, the Distinguished Lecture Series lineup draws from some of the deeply talented researchers in our community of faculty, former faculty, as well as alumni. Today's special talk features our very own Professor Raquel Ortazan, who is really a testament to the innovation and talent in U of T and the Department of Computer Science. With that being said, I would like to hand it over to Professor David Fleet, who will introduce our distinguished speaker.
I've got notes. It's a great honor for me to introduce Raquel. I've known Raquel for quite some time. As the slides indicate, she is Professor of Computer Science at the University of Toronto. She's also the founder and CEO of Waabi, a very high-profile startup company developing fully autonomous AI-powered trucks. Her research is well known to many of you. I suspect it spans computer vision, machine learning, and robotics. In these fields, she's made fundamental contributions for which she's received numerous awards. And unfortunately, there are so many, I can't list them all, but I have listed some here, and I'll read them so I don't miss any. She has research awards from NVIDIA, from Google, from Amazon, Best Paper Awards at the top international conferences in her field. And this includes the 2022 Longat-Higgins Prize in Computer Vision, and she's also won an NSERC Stacey Award. And these are all remarkably prestigious awards to win. She has been appointed to the Order of Ontario and very recently was named Fellow of the Royal Society of Canada. In 2023, she was named one of Time magazine's 100 most influential people in AI. And the list goes on. And as I say, I won't name them all. Raquel first joined the faculty at the University of Toronto in 2015, but her association with the Department of Computer Science and the University of Toronto dates actually well before that, back to 2005, when as a PhD student, she came to visit and work with the computer vision group at the university. And she has maintained a working association and a true friendship with many of us in the computer vision group ever since, during the remainder of her PhD at EPFL, throughout her 2 postdocs, one at MIT and the other at Berkeley, and indeed as an assistant professor at TTI in Chicago, all before coming back and joining the Department of Computer Science in 2015, for which we're tremendously grateful. The title of her talk today, which is evident again on the slides behind me, is Bringing Generative AI into the Physical World. Raquel.
It's really a pleasure to be here today, and it's actually January 2014 when I moved to Canada. It's been a decade now, and as a Spaniard, moving to Canada in January was a really, really interesting idea. As I learned to appreciate winters, the 10 years to come. One of the best, or probably the best idea that I had, as a professional was actually to leave the US and come to Canada. And it's been, I came here for U of T as the Center for Innovation in AI. We've seen, I guess, last week, Geoff Hinton receiving the Nobel Prize, something that he absolutely deserves. And, it was a great moment for him, for the department, for the university, for Canada, for the computer science, world in general. And it's been an incredible 10 years. And, there is a lot of things that, kept me busy over the last 10 years. And what you're going to see today is really the culmination of almost 2 decades pursuing this idea of building self-driving solutions that can really transform the world as we know it and really bring so many goodness to our world, from democratizing transportation to robustifying our supply chain to enhance safety, etc. Okay, so let's get started. All right, so today, and the title said that, right, it's going to be about generative AI, right? And I think by now everybody should be familiar with this idea that you can build an AI system that is able to generate new content. And this new content can be things like videos, can be images, text, etc. And these systems became very, very popular, particularly since November of 2022, with the launch of ChatGPT, that really revolutionized the way that us humans interact with computers. And it's based on this very simple idea that you can discretize your language in terms of a set of tokens, and you can learn about this language by simply predicting in an unsupervised fashion, without any human supervision, what is the next word that is going to appear in a sentence. Right? It's a very, very simple concept, but if you scale this, suddenly you have a massive impact in the world. Go figure. And whenever you look at ChatGPT and any metric, whether it's performance, whether it is the ability for companies that were launched after the revolution, etc., in any of these metrics, it's amazing how it's off the charts in terms of something that we have never seen before. One of my favorite metrics is what you see on the screen here, which is the time it took for different companies to reach 1 million users. Right? I'm sure that most of you use Netflix or one of these providers. It took 3.5 years for Netflix to actually reach 1 million users. Right? Airbnb, 2.5 years. Facebook, 10 months. If you look at ChatGPT, it took 5 days. And I think that the number of active users is going to be 250 million, if I'm not mistaken, this quarter. Right? So it's mind-blowing the penetration that this technology actually suddenly had. Now, when you look at what is it that actually enabled this revolution, obviously there is all the foundational work that was done in the field, including the amazing work of Geoff. But there is really like 3 things that make this revolution possible. On one side is data, right? It's the fact that we have digitalized the world. The access to the internet was fundamental for large language models to actually become what they are today. There is also compute, right? There's been a lot of progress, and it's not by chance that NVIDIA is a $3.3 trillion company today, and kudos to my friend Jensen, that has done a tremendous job in terms of scaling the company and really building the next generation compute. And the last bit is really some algorithmic improvements in that were carried so that we can really scale these systems, right? So it's actually 3 very, very simple things that enable this revolution. Now, when you look at, the digital world has been transformed, right? The next question to ask is, what's next? The world is really about to change, and one of the things I will argue today is that if you look out the window today, particularly here in Toronto, you don't really see robots and things like this happening, but in 5 to 10 years, they're gonna be everywhere, right? So the next revolution is really, can we bring this technology to the physical world and deploy it in a safe manner? Okay, and this is what today is gonna be about. Now, if you look at moving generative AI from the digital world to the physical world, there is actually 3 challenges or properties or things that are not as important in the digital world, but they are fundamental that you actually really nail in the physical world. Okay? So you need to really move and transform and develop new technology to really push generative AI in these 3 different directions. The first one is generalization. Right? In machine learning, we talk a lot about generalization, but this is an extreme form in the sense that you are never going to have enough data to see everything that potentially you're going to see when you deploy the system. And when you work on physical systems like self-driving vehicles and other robots, having mistakes have potentially catastrophic consequences. So if you are, your robot is deployed and it's going to see something that it has never seen before, it has to do the right thing. Right? So it needs these extreme ways of generalization, and you need to make sure that you train the system for it, you evaluate the system for it, and it's always, it's able to do the right thing no matter what. So that's one key difference with respect to an LLM, where if he makes a mistake, well, you just, poke it with, a different sentence, etc. Right? And then you little by little interact. This is not the case in the physical world. The second is actually efficiency. And I will argue that there is 2 different levels of efficiency that are tremendously important. One is that since it's a safety critical system, all the compute actually runs on the robot, on the vehicle. So you need to develop technology that is super fast, because reaction time means, it's not gonna be safe. It takes 2 seconds to decide what to do, right? You're gonna end up in accidents. So it has to be a very, very efficient architecture that you're able to deploy with low energy in terms of the robots. But more importantly, and this is very important of the world that we live today, is I will argue that we need to also have an approach to sustainable AI. Where are things going? It's like larger and larger models, billions of dollars to just train a model, data centers that have the power of New York, more and more data centers, more and more power. There is no resources in the planet, right? So we need to move away from that to also have very efficient ways to train these models. Okay? So it's not just about the deployment and inference, it's also about the efficiency on training. And the last key element is something that I alluded a little bit with generalization, which is the fact that you're going to deploy something, that, a robot, a physical robot that is going to interact with humans. So it's very important that this system is actually safe. But that's actually not enough. Why is it not enough? Because prior to deployment, you need to prove that indeed is safe. So you need to build technology where you can actually prove safety. Okay, and that is a challenge when you think of using end-to-end architectures, etc. All right, so over the last 2 decades, I've been looking at this idea of building foundational models, single AI systems that are able to really reason and do all the tasks necessary for applications from perception to action. And when I started Waabi 3.5 years ago, the kind of technology that we were looking at could be applied to any use case, any form factor, humanoid robots, warehouse robotics, etc. But I decided that trucking was going to be really the first application where deployment at the scale is going to happen. And today, it's more and more clear that it was the right bet. So let me tell you why long-haul trucking, this is our trucks driving, that you can see driving autonomously in Texas, why this is really the first application that makes sense for scaling this technology. So if you look at the pain points of the industry today, are pretty bad, right? So you have a tremendous economic opportunity, and I know this is more of an academic audience, but this is still cool to say this is $1 trillion opportunity. It's the opportunity to build the next NVIDIA, right? There are not that many opportunities like this. But if you look at the issues that you see with supply chain today, is that there is a driver shortage, and this is, I have US numbers here, but it's the same for Canada. Where yes, in the US, right, so there is 100,000 drivers missing. Nobody wants to be a long-haul truck driver. It's actually a really difficult job to do. They go, on the road for weeks. Oftentimes, they don't even have access to bathrooms. Can you imagine this? You cannot take a shower. You cannot even, go to a regular bathroom for days and days in a row. Right? So this is what I call an unhumanized job. Right? So this is the jobs that we can actually help with automation. There is obviously safety concerns, and this is quite interesting because the ADAS field has advanced a lot. However, the number of deaths on the road has stayed constant or increased over time. And cell phones are actually one of the reasons why this happens. And then last bit is environmental impact. When you look at the supply chain today, if you look at trucks, 20 to 30% of the miles driven by these trucks, the trucks are not driving anything. This is for human drivers today. Right? So there is a massive opportunity to make that much more efficient and much more sustainable. Now, from a customer perspective, right, you might think, like, why do I care about self-driving trucks if I am Amazon or I'm Werner or one of the big shippers, Bison, Trimac in Canada, etc. Well, the reason why is that potentially you can have a much cheaper product that is much more reliable, or you can actually utilize much more. Humans have hours of service. There is only 11 hours that you can actually drive. If you look at today, on average, humans only drive 6.5 hours. Imagine you buy a truck and it's only utilized 6.5 hours. There is a tremendous opportunity to utilize that asset, right, and build less trucks. And obviously safety and sustainability, right? So a tremendous opportunity that this technology addresses. So you're probably thinking, where is the industry today, right? Where, have we seen products out there? So for self-driving trucks, there is not a single product that anybody has been able to launch. Okay, there has been a couple of demos here and there, but there is no product where reliably you can remove the human driver and have a machine that can actually drive, on public roads without a human on board. And the reason why, and oftentimes people ask me, is like, why is self-driving so difficult? And why it has been so underestimated is because there are so many things that can happen when you actually drive on the road. Just think about, for those of you that drive or have been driven by somebody, like, despite for example, highways being structured, there is so many rare cases that actually, when you look at the amount of those rare cases, it's quite often that you see an oops, or oh wow, what is this? I have never seen before. So it's actually pretty hard for machines to do this task. And if you look at what the industry has been building, which is what is called today AB 1.0, it's a very hand-engineered approach where you need to explicitly incorporate knowledge for the system to reason about it. And that's something that you need to think about all the possibilities prior to actually seeing those possibilities is impossible, right? So what you end up doing is you have this very costly loop where you go on the road, you drive millions of miles, you see issues, you try to develop a new model, you incorporate in your really, really brittle and massive software stack, and you continue iterating. Okay, and the players today, our biggest competitor spends $1 billion per year, with a B, $1 billion, right? And they're still far from launching, right? So we need something that is different than this. This is not gonna cut it, right? So when I started Waabi 3.5 years ago, I saw a tremendous opportunity to really go in a very different direction, which is if we can unleash the power of AI to build a single AI system that is able to generalize to be efficient and provably safe, we can disrupt tremendously the self-driving industry. Okay? So this was the idea behind Waabi, and this was prior to the ChatGPT moment, right? So now it has become more and more clear to everybody that indeed that was the right direction, and this is where the field is going today. All right, so as I mentioned before, right, this is not an idea that happened overnight. I spent the last 2 decades trying to build these single AI systems that are able to reason like humans do. Okay, so let me tell you a little bit more, going a little bit more on the details of some examples of some of the foundational models that we actually developed. And what I'm going to show you here are baby versions of what we have in production, okay? But at least it gets you some idea of, the kind of technology that you can build when you actually try to really bring this technology to the next level. Right, so it's this idea of foundational models, right, that you can have a single AI system, right, that the same as large language models are learned by predicting the next word, right, in a sentence. You can do the same thing by predicting what is the truck going to see over the next few seconds, right? So that's the equivalent, right? And the idea is that by just unsupervised, just driving around the world and then learning about it, you can actually discover abstractions of what objects are, things like uncertainty, etc. It will all be discovered automatically. Okay? It's a very, very powerful approach. So let's look at, I'm going to show you 2 examples of these foundational models that we've done. So you get a flavor of the kind of technology. So this is the first kind of foundational model that we made public. This was a year ago. And the idea with Copilot 4D is to build a 4D foundational model. 4D is 3-dimensional space and time, okay? And in particular, we built this particular technology by looking at, can we learn about the world by predicting how LiDAR mounted on top of the vehicle is going to observe the world in the next few seconds. If you want to learn to do that, then you need to understand how the world evolves, what are the different things doing, how are they going to move, etc., without anybody really describing categories, etc. Right? So we build an architecture. This is very black boxy, but it is very, I guess, high level. But the idea is that you can discretize the world, and you can create a world model that is able to predict on that discretized world, and then you can render that world in order to create the observations back. Okay? So very, very similar to the idea of foundational models for large language models, but in the 4-dimensional field. And what was interesting here is that both the tokenizer as well as the renderer is something that we needed to really come up with a very different way to do this, because obviously what's done for language is already discretized, right? So we needed to come up with much more sophisticated ways to do this. So in terms of the tokenizer, you will see we bring some discrete tokens that are spatiotemporal, and in case of the renderer, we use our simulation in order to, inspired by physics, learn to actually render the world. Okay? So instead of having a word here will be like a little spatiotemporal token in the space, and you have a grid of those tokens that you need to predict the next word is next grid of tokens in the future. Okay? That's kind of the analogy. So it's one more dimension that you are used to otherwise. And it turns out that actually this worked really, really well, and this worked much better than traditional approaches in order to do things like forecasting the future, etc. Okay, so this was exciting. We were into something interesting here with this. However, this type of model had 2, I would say, 2 difficulties. One is the fact that, or 2 challenges. One was the fact that we have continuous and high-dimensional sensor information, and when we were predicting that, it's not really useful for the task of driving. Okay, you might predict the future, you might do some counterfactual reasoning, but it's not something that you can take and then, okay, take this thing and then go and drive nicely on the real world. So we look at a different type of foundational model that is built on top of better understanding of what the world is and how our sensor works, that actually really give us this ability to really handle the unknown really well. Okay? So what you see over here, if you haven't seen what LiDAR actually sees, this is a representation where it gives you points in 3-dimensional space with some time associated with it. So it's spinning typically, and then it's seeing the world by launching rays, and then when they come back, you can actually measure the distance. That's roughly what it does. Okay? So you get these sparse kind of representations that are really good in 3-dimensional space, right? And what we look at is, what is the best way to utilize this information? It turns out that there is a lot more information that you can get than just this notion of there is a point, is that if you can actually launch a ray from the vehicle to any of the points that you observe, what you have is that when you hit something, it means there is something there, right? So there is going to be some occupied space over there, so that's what you know. But what you also know is that if you manage to hit something far away, it means that there is nothing in front. So you also have like negative supervision in terms of there is nothing over there. And with this very simple idea, you can actually build much more, I will say, informative loss functions for those of you that do AI in the audience that enable you to learn much better representations of objects, okay? And in a way that is more useful for self-driving, okay? And the idea is that this is going to enable to build these unsupervised 4-dimensional occupancy fields, okay? So let me show you how this looks like. Cool. Right, so by just having supervision on the left, we're going to be able to predict the future and predict the future in a way that we understand what is occupied versus not. And this is a very useful representation for any robotics that has to navigate in the world, whether it has to navigate in 3D or it has to navigate in 2D. Okay? And there was some interesting, some really interesting intricacies in how we do this by building implicit representations in this type of model that enables you to have infinite resolution. That was a big deal in terms of time, memory savings with respect to everything else that we have seen in the industry. So this is, some of the best actually work I've done in my career, which is, you haven't seen this paper, and the follow-ups are very, very exciting. Right, so we are able to predict these occupancies. We are also able to, you can learn to render, so you can predict what the later also will look like, and you are also able to do things like semantic occupancy and other tasks that are very, very useful for driving. Okay, so let me show you some videos so you can see. So on the left-hand side is a full view from, from the sky looking down. In the middle is what unsupervised the model is really learning in terms of, the space in front of you, and you see that, it's able to handle like very, small structures like cones, pedestrians, etc., really, really well. Learns the concept of objects, as you see here, learns the concept of occlusion, uncertainty in terms of the size of and shapes, motion, etc. So it's fascinating what you can do actually unsupervised these days. You can learn to handle things like, this is a real example of our truck driving around, where we see here, I think it's a couch on the highway, right? These things actually happen, as I mentioned at the beginning, more often than you think. And then we need to build representations that can understand that it's something in front of us and we need to do something about it. And in terms of, metrics, etc., no matter how you look, this creates, very, very much better for performance than anything that we have seen. Cool. You can also transfer this to do more semantics if you have labels for, and then you can just change a little bit the architecture to be able to do this, and then you end up with something that can learn from almost no example, as you see here. So it's fascinating, right? With as little as even 10, 100 examples, you almost get on par with something that uses 20,000, 200,000, whatever it is on the chart, right? So. You can really break the law in terms of how much supervised data you really need in order to learn to perform tasks that are very, very complex. All right, so how do these foundational models really piece together with a system that does decision making? Is that what you see here is the architecture of Wabi Driver, where, again, staying pretty high level, but the idea is that your foundational model can actually learn to interpret the scene in a way that you're not hard coding what it is that you're seeing, right? And this can be used with a very fat interface to actually perform reasoning about what are all the things that the vehicle can actually do, and then the vehicle can actually take the right decision by understanding what are the consequences of every action and which one is the safest action. So that's the underpinning single AI system that runs within Wabi Driver, which is the virtual driver that controls the self-driving trucks. Okay? And interestingly, since this is trained end-to-end, you can actually have sensors in the decision-making, so you don't lose any information. You can have very, very sophisticated interfaces that are very different from what you will see in a traditional approach. Okay? And this ends up working really, really well. Now, the good news of this architecture I just showed you is that it's interpretable, so that you can actually validate and verify its decisions, something that is very important for regulators in order to trust that the system is going to do the right thing, and if for whatever reason it doesn't do the right thing, you can look back and say, this is why the system got confused, this is what it thought. So you have this explainability that is very important for the safety critical systems. And this is really contrasts with the type of approach that you will see these days with Tesla, with Wave, where the idea is that they have a black box architecture where there is no interpretability, where it's extremely difficult to impossible to validate and verify, versus it's not the case for us, right? While it's still an end-to-end system. And with the black box architecture, the other thing that is actually really problematic is that you need a lot of data for training the system. And no matter who you are, even if you're an OEM, you have millions of vehicles deployed, you still don't have enough data, right? And obviously you don't have enough data of safety critical accidents, things like this, where you need to make sure that the system does the right thing, right? So you are very, very skewed in terms of you see a lot of regular driving, but you're not gonna cause accidents on purpose, right? That will be unethical. All right, so something that oftentimes people ask me is whether Waabi uses or doesn't use high definition maps. So I'm gonna give you my 2 cents about what we do and why we do what we do, which is that for safety, we use multiple sensors, LiDAR, camera, radar on the vehicle, so that there is redundancy between them. And for safety, we also use high definition maps. We build our own technology for everything that we do, including the high definition maps. And oftentimes people don't want to talk about high definition maps, or they don't want to use them because they don't scale. These are like very precise maps that typically are drawn by humans, and it's very expensive to create them. And then you need to maintain them, and it's a mess, right? Typically, it's $1,000, $2,000 per kilometer per mile, depending on the provider. So as you can imagine, if you want to deploy your technology in the entire world, that's massive in terms of the capital that you need for these maps. So what we did with Waabi is with our GenAI technology, we can create these maps basically automatically, and then just have a human to validate them at the end. So that enables us to do it super, super fast and super cheap. It only takes or costs us $50 per mile to actually create these maps. Right? So it's massive the efficiency that you get thanks to GenAI. All right, so I talk a lot about foundational models, having an AI system that is able to think and reason like a human. But probably one of the underlying questions is that, so you talk about the design of that, but how do we actually teach the autonomous system to perform the right thing, particularly in safety critical accidents, right? And how do we, we talk about this provably safe, how do you know that this system is ready to be deployed and is safer than a human, right? So we're gonna answer this question with the same piece of technology, okay? And this is actually a pretty difficult question, right? So what the industry is doing today is just going and driving in the real world and then hope that they will see enough to teach, to validate, to do whatever, right? So that's not very scalable, right? And as I mentioned before, it's not that you're gonna create accidents on purpose to see whether the system actually does the right thing. So we need a different methodology, right? So, if you think about it, right, what you would like to do is have the ability to create all those situations, including the safety critical, but without the risk of putting a fleet on, on public roads at that scale and with all those situations, right? So what's the alternative? The alternative is to go to a virtual world simulation, right? And the idea is very, very simple, which is if you can create a simulator that is the same as the real world, with the same level of fidelity where you can simulate everything, and then you have also a way to score how well you do on those simulations, then suddenly you have the last bit of, the last key that you need in order to solve self-driving, right? You solve the data problem. And as you know, in AI, data is the majority of the question, right? Your model is as good as your data is. Okay? So I have a question for you guys, which is you've been, looking at maybe some of these scenarios and whatnot. And my question to you is, can you guess which ones are simulation versus the real world? Some of you have seen this. Maybe some read the Bloomberg article that actually spoiled what the answer is. So don't answer if you have seen this before, but if you haven't, any guesses? Yeah, go for it. Why do you think so? Don't be shy, don't be shy. Just express what you think is. Yeah, so this bright color is what you get typically when there is sensor saturation. Okay, so actually that is typically a real phenomenon, typically. Any other thoughts? Yes? So it's what, is sim or is real? It's real because you saw humans, cool. Any other guesses? Maybe somebody has been in San Francisco, can guess, where these places you have seen, you've been in Embarcadero, there is, some areas, yes? Yes, go for it. All right, somebody has read Unisim, right, has seen this, and the authors of Unisim are actually somewhere close to you, so I should change the videos here. So they're all simulation, nothing is real, right? But there is no way to tell, and every time I ask this question, people point to different things. And it's interesting to hear the why. Sometimes people say, oh, it's real because it's imperfect, right? And compared to game engines, that's typically, they look very cartoonish, right? When I started Wabi, the idea was, can we use generative AI, at the time called AI First, to create a simulator where it's the same as the real world? If we can actually do that, then suddenly we can actually solve self-driving. So the simulator is the first thing that we built. So let me tell you a bit more about the simulator that is underpinning this thing. So we call it Wabi World. But before telling you what we do, let me tell you what the others do so that you can see a contrast of approaches. So if you look at the industry today, there is 3 types of simulation tools. These are 3 very different tools, pieces of software, and typically everybody in the industry uses at least 2 forms of simulation that are reflected over here. So the first one is called log replay. And to be honest, I don't know why this is called simulation, because you're not really simulating much or anything. And the idea is that you capture data in the real world with your self-driving vehicle driving around, whether it's by a human or a version of the software, doesn't matter. But you capture the data, that data is static, and you're going to replay it. And then you're going to look at whether your next version of the software, whether it's actually doing something different or similar or doing the right thing, whatever that means in that context. Okay? But that software doesn't have the ability to control the vehicle because the data has already been captured. Okay? So the analogy is, I want to learn to play tennis by watching your favorite tennis player, whoever it is. Okay? So you're not going to get very good like that. You need to practice, right? You need to actually do the right thing. Like be able to see, if I hit the ball, where is it going, right? So this is not a good way to evaluate. It's not a good way to train the system, right? Because it doesn't understand the consequences of its actions. The second type of simulation is something where we are going to be more playing than watching, but we're going to start with a high-level abstraction of the world. This is typically in the form of, so it's the middle thing, middle video over there, where it's typically this representation that has bounding boxes or these squares, right, representing vehicles, and we're going to test whether our motion planner, which is a small part of the software, is doing the right thing under ideal conditions. So it's controlling, right, and you're looking at interactions, but you're only evaluating a very small piece of the software, and under very good conditions, like ideal conditions or very simple noise, right? So that's also not very good at telling you how well the system is going to behave, because the ideal conditions never going to happen. It's like saying, oh yeah, if I solve perception, I can actually do perfect self-driving. Well, you're never going to solve perfectly perception, right? Even humans, we cannot see oftentimes well, right? All right, so that's the second type. So that's also not great. And the third type is something that we see a little bit more now, and it's typically in beta, not really used. But the idea is that if you can have artists create these 3-dimensional worlds, and then you can use game engines or physics-based simulation to render those worlds, then you can actually create data for perception. Perception meaning the first bit of the software. right? So, but the problem of this is that, artists generating the content is extremely expensive. Depending on how good your scenes are, even one scene can cost you between $20,000 to $100,000. I think the Avatar world costs $100 million, something like this. So you can imagine that that's not scalable, right? You're not going to be able to test everything. And then when you render, it's either extremely expensive and not realistic. And if you use a game engine, it's fast, but it looks extremely cartoonish. So this is not really used for augmentation of data. It's only used for really, really rare classes, things that you almost never see. Okay? So that's simulation today is very, very limited. And as you see, it's not really a replacement for driving in the real world. When you drive in the real world, you do very different things. So let's look at what are the characteristics that you need of this simulator. Right? So you need to be realistic. We talk about it. You need to be controllable so that you can generate all the possible situations. It has to be diverse, right? Because you need to test under all possible conditions. It has to run fast because you want to evaluate and train the system at that scale. It has to be immersive, which means that it needs to mimic how the system is seeing the world and acting on it, right? Immersive meaning that it has to see, right? So you need to simulate the sensors. And it has to be reactive because if you're doing certain maneuvers, all the agents need to react to what you're doing and react to between themselves. And last but not least, it's also very important that it needs to provide feedback. What this means is that you need to get metrics for all your simulation outcomes and in a trustable manner. Actually, typically simulation systems don't give you data or metrics that actually you can just directly take and you believe what it's there, right? It sounds mind-blowing, but this is what it is today. All right, so how did we build Wabi World? So we build it like the real world. So let me explain how the real world works, and then I will explain how Wabi World works, okay? So in the real world, you are driving, you're a self-driving vehicle, right? You're a robot, you are driving in the real world, and you have all these sensors around you, whether it's cameras, radar, etc. So every fraction of a second, you are seeing the world from your perspective, right? With all those sensors. Now, once you actually you receive the information from all the sensors, you're going to run your entire software, right, to decide of what is the action that you're going to take, right? Then you give that action to the actuators, right, in order to steer, brake, accelerate, etc. And once you give that information, then basically the physical vehicle is going to do something, right? And typically what you intend to do is a little bit different than what happens in reality because of friction, wind, gear changes, all sorts of physical phenomena, right? So there is a little bit of a difference there. And then you repeat this every fraction of a second. At the same time as you are driving, everybody around you is driving, right? Is reacting to each other, etc. Okay. So we build the same concept with GenAI modules, okay, where we're going to be able to, we have this, think of it as a 4-dimensional neural world. It's a bit more sophisticated than just a 3-dimensional world or just geometry. It actually has a lot more information than that. And you're going to simulate in real time the sensors, how they see it. You're going to execute the entire software so that you can actually test the entire system, right? That's very different from this motion planning little tiny thing, right? And we're going to also simulate the dynamics, how the perturbations due to all these different physical phenomena. Okay? And at the same time, as we are doing all this, we're also going to inject latency, simulating the time it takes for our compute to actually compute the different things that it does. And that's important because depending on that time, your reaction to other actors is going to change. Okay? And this is actually very important for safety. And at the same time, as we are doing all this, then every single vehicle, every single pedestrian, every single animal, whatever, is an agent, an AI agent that lives in this world that is going to react to everything. Okay, so we really mimic, how the world works, and all within GenAI, so you can create all content that you might ever want. Okay, so very, very different design, very different simulator. Okay, and you're probably thinking, how do you end up with something that looks so realistic? Are you doing like Sora-like? So it's very different from OpenAI video generation, right? The architecture that I showed you before. And it's built on this idea that if you are able to automatically clone the world in a way that is very realistic, and then you can re-render that world in a composable and modifiable manner, then suddenly you have all the content, you have everything that you need to really generate this at scale. Okay? So that's how the content for Wabi World is built, and then you can manipulate that world. You can place actors in places that weren't before. You can add things like cones, construction. You can remove things that were there in the first place. You can drive in this world differently that you ever capture and see from any perspective. And that's actually what enabled us to really have this super high quality simulation. Okay, so let's see it on a video. On the left is the real world, on the right is the clone, the modifiable clone. Okay? So it's modifiable, we can remove things as you see over here, and it's able to understand how the world will look like if you remove those things, because they're actually physical things. We can also modify what the real vehicles or agents or pedestrians were doing in the first place to generate new situations, right? Like in this case, we are aborting the left turn, and then we are actually creating a situation where we need to slow down, otherwise we're gonna collide. No matter how you saw that scene, when you capture the data, right, with just one pass, we can re-render that scene from any perspective. This enables us to change the location of the sensors, to capture the data with a passenger car and then simulate our trucks, to optimize for our hardware in simulation before we even build the trucks in the first place. Right? And that's massive what this actually gives you for self-driving. And as I mentioned, everything is composable, so the vehicles that you see on the right came from somewhere else in the world. We can drop them there to do things that they have never done before. And it's all in a way that everything is reactive to you, and then you are reactive to it. You can simulate any sensor available in the market, any possible LiDAR, any possible camera, etc. So it's a massive, massive step forward in terms of really solving self-driving by solving the data problem. Cool. So just a little bit, a couple of details on this. So the way that we can generate this content is that we can do it by composing and modifying clones. I saw you some examples on the video, right? You can change also time of the day, weather conditions. You can change what is in the scene, what the actors are doing. You can generate new content from something that is not in there. You can actually have the user that specifies precise simulations or only precise things for a subset of actors. This is actually really useful when you're interested in testing specific things. You can run the simulator in adversarial mode, where the simulator is trying to trick the software to find its deficiencies automatically. And this is very, very useful, so that you don't need to run billions of simulations to understand that you still cannot handle this thing, generate me more training data, or yes, enable the safety driver to understand what Wabi driver cannot do well yet today. And then you can do all combinations of these things in a way that is very scalable. And we have also a zoo of models, and this is very important for how the actors behave, because no matter how humans react, you want to always do the right thing, right? So it's very important that you don't overfit to a particular system. Furthermore, we can prove the realism of the simulator for the first time. And this is really, really exciting, because since we can clone the world, we can use this to seed our simulations, to unroll them fully automatic, and then see whether the same software driving on simulation and driving in the real world do the same thing. So we can compare the outcome in a per manner, and then do this at the scale, and then see and evaluate the realism of the simulator. So this is a huge step forward into validating and verifying simulators. And finally, we have this simulator that can really handle or have all these different characteristics that we wanted in the first place, compared to everything else. All right. So now Wabi doesn't need to have hundreds, thousands, tens of thousands, millions of trucks to see the world. And this eliminates, obviously it's much more capital efficient, it's much less risky, and it's a way to really expose the system to unavoidable accidents and other things that will be impossible. Okay? I haven't talked much about hardware. I focus a lot in AI because I thought that was probably where everybody would be interested. But that's one of our self-driving trucks. We actually brought it last June to Toronto for the unveil of one of our biggest milestones. And if you are in Texas, you can see them driving autonomously on public roads. But the way that we build this is in a way that is very easy to integrate at the factory line so that you have the scale together with the OEM. So you vertically integrate, and our hardware, as I mentioned before, is redundant redundant camera, LiDAR, radar, as well as compute, which we actually are building the compute for the trucks together with NVIDIA. Okay. All right. So last bit that I want to show you is about safety. I mentioned that you need to deploy something that is safe. And in the definition of safe, it's not just about a system that doesn't collide. Okay? Oftentimes, that's what is used in the industry, but that's not enough. You need a much more robust way of defining defining safety. So you have to be safer than a human. You need to be able to prevent situations in the first place from occurring. You need to be able to improve safety not just for yourself, but for everybody that is on the road. You need to have minimal disruption to traffic, right? If you stop in the middle of a highway, that's actually pretty dangerous. You need to comply with the laws of traffic, but this is very important that if safety is at risk, you can violate the rules of traffic, right? Some self-driving players are saying that you should always satisfy the rules of traffic. That is not safe. Let me give you an example. Imagine you don't have enough time for, something happened to the vehicle in front of you. You're a self-driving truck. It's a car. It can actually brake much faster than you. And there is no way to avoid the collision. It wasn't your fault. Something happened to that car. And there is a traffic light that is red. You probably want to avoid and get into the intersection to save the life of that person, right? And not comply with that rule of traffic, but for safety only. Right, so it's very important that we go beyond that idea of rules of traffic is what verify AI. That's just not the right thing. Then you need to adapt to conditions, whether it's it's raining or whether you don't see well, and response to the unknown. Right, very, very important. And I'm going to show you an example of this is actually our self-driving truck doing the right thing, violating the rules of traffic to save a life. Okay, very, very important that you actually have this ability. All right, and in order to prove the safety case, simulation is a must, and only a simulator like the one that I show you today enables you to actually do the safety case. All right, so what I show you today is this idea of you have a foundational model that drives the truck, you have a simulator that is really able to train and test the system at a scale. And for the first time, it's a system that is end-to-end trainable, that it can generalize, that is efficient, and is probably safe. Okay? So let me show you in 2 seconds where are we in our deployment. So I started the company in 2021, and here are the major milestones of Waabi. And we built first the simulator, then we built the trucks. Then we launched them on public roads, and today they are doing commercial runs with some of the largest shippers of North America. Exciting as well in our is what's coming next, which is next year we are launching our trucks with no human on the tractor. This hasn't been done before, and in as little time as 4.5 years, we will be able to do this. And it's amazing thanks to this technology. There is no way that you can go with a traditional approach and do it in a fraction of the time with a fraction of the capital. And this is very, very exciting to actually be doing this from Canada, which is at the epicenter of AI, right? So bringing all that innovation, but now transforming the physical world and transforming the industry today. And last but not least, for those of you that are entrepreneurs on the room, something I will say as well is you need the vision, the technology differentiator. You need the amazing team behind Waabi, which is the best thing. It's really that team that is, incredible human beings. And you also need the right partners and the right investors. Okay? One of the exciting things that we announced lately was our Series B fundraise. Fun fact, our A and B were the largest in Canadian history. And as you see here, the backers of Waabi is best in class on AI, logistics, the Canadian ecosystem, which is very important for us, proud Canadian company, OEMs, and financial investors. Okay? So if you're interested in building a company, speak not just about big capital, 200 million, that's great, right? But it's more important who is in your cap table, who can actually help you build the best possible company. Okay? And these folks around here are extremely bullish about what we are actually building. All right, so I will finish with just a thought for you, which is that what I showed you today and self-driving trucks, they are coming, they will be on public roads next year without a human, but there is so much more that this technology can do. And Waabi is going to do many more things than just trucks. Whether it's humanoid robots, robotaxis, warehouse robotics, drones, you name it, robots are here to make our lives much better, much safer, right? Much more human. And I'm really excited to be able to be doing this here. And if you're interested, we are hiring, so let me know. Okay, thank you.
The online live stream portion of the event today. Thank you, and thank you to everyone who has tuned in online to see the presentation.
Thank you.
What we will do next is, for those present in the room, we have 15 minutes for question and answers. So if people have questions, I think there's a microphone have questions. If anyone's got questions, this is the time. Yeah?
Hey, I have the mic. Thanks, Raquel, for a really engaging talk. I had a question. How do you solve, the self-driving truck version of the trolley problem?
Yeah, and I guess there is no more online, so I can talk more. This is not recorded. So that was just a joke, okay. Sorry, my comms team is probably buzzing now. The trolley problem, for those of you that don't know, is imagine you come to a situation where you need to choose between hitting person A versus person B, right? So at Waabi, the way that we are, what our system is trained to do is to minimize the bad outcome, okay? And I don't feel that I can say whether your life, and I don't know where you are because I don't see anything with these lights, that your life is more or less worth than anybody else's life, okay? So I will not put a price into human life, this particular life versus that. If governments, regulatory bodies want to do that, there are ways to incorporate that into the system, but I will not be the one doing that. So right now, for us, is minimizing the bad outcome. And the good thing about a self-driving truck is that we are actually not carrying a human, so we can always take the hit versus somebody else. Whoever wants to go. I guess the microphone will choose.
Hi, I was wondering if you could talk a little bit more about the sensors you have on the trucks, especially for longer distance. Since LiDAR only has a short distance of visibility, how would you be able to predict and account for an object on the road that's further away?
Yeah, so in the truck, I don't have a frontal view there, but in the truck, there is 4 sensor pods, 2 on the top sides, 1 on the grill, that is for looking nearby. The 2 on the sides are looking mid-range as well as close to the truck. And there is in the center, the long-range pod. Each one of these pods have LiDAR, camera, radar. Some of the pods have multiple LiDARs. As it relates to whether the LiDAR can see far or not, the long-range LiDARs today can go up to 500 meters. So actually they see quite a bit far. But with radar and cameras, you can see very, very far.
And
so sensors are not a problem today.
As a follow-up, is this data also included inside your simulations?
Yes, everything is, yeah. Every single PR at Waabi goes through simulation in order to land the set right. The Waabi world is really the underpinning of everything that we do.
Not sure if that's on. Oh, it is. Great talk. Thank you for the presentation. Just wondering, in a train of trucks scenario, would there be any cooperation between agents where a lead truck might pass data to a truck that's behind it? Thinking aerodynamics and having trucks very close to each other to maximize efficiency.
So what's the question? Is the question about convoys, or is the
question is about cooperation between different trucks. Would they share data with each other to inform them of the road ahead?
Yeah, so I mean, right now, I guess the sizes of fleets of self-driving vehicles is very small for V2V and cooperation to actually make a dent or anything like this. In the future, you could do things like this. You know, a few years ago, many people in the industry thought that convoys, which is many self-driving trucks were following a human-driven truck, would be the way to go. Today it's very clear that that's not a business model that will ever work. But for you know, Waabi driver trucks, they can actually share information over the air already. So that's a way that you can do things. But in terms of fuel efficiency, yes, just for context, is typically self-driving trucks are like 10 to 15% more fuel efficient than humans. Humans are actually not that good at that. But we are not doing right now anything specific for optimizing for being a fleet and what we can do there, because if you look at the routes, they are pretty dispersed typically in self-driving. Whoever wants to be next, I don't know.
Yeah, so for the reasoner module that takes inputs from the world model, is the world model like trained to sort of kind of predict what the world would look like given what it sees and some action, and the reasoner module sort of performs sort of like a chain of low-level motions to look for what the best world state would be?
Yeah, so we haven't made public what the reasoning model does. It's not a chain of thought model, but you can think of it as kind of next generation of that. Yeah, sorry for not giving you the secret sauce.
Hi, thank you for the talk, Professor. So I'm interested in your opinion in using simulation to enhancing some reasoning capabilities. So I'm personally interested in some brain science, and for humans, we are doing simulations all the time to access the consequence. Especially during the reasoning, we do something like mental simulation. So right now, the agent seems to missing this kind of subconscious simulation concept. And I'm wondering, like, for your simulation, it's like some physical simulations and some graph simulations. That's really fundamental simulations. What's your thoughts in developing more simulations? First question, do you think simulations will really help enhancing the reasoning capability? And if so, what are some of the foundational simulations you think?
Yeah. So okay, maybe I'm going to say more about this reasoning model than I intended to. So that reasoning model is a little bit on the direction of what you're saying, where it can understand what are all the things, all the actions that it can perform. And these actions are longer term. It's not just one frame kind of action.
Right.
And it can understand the consequences of the actions. And in order to understand this, maybe you can do things like simulations, but they are very different types of simulations than what you see with Waabi World. So the reasoning does something along the lines of what you're saying, but I don't call that simulation.
But for like agents, for example, LLM agents, do you think there are some other fundamental simulations?
I mean, you can run the agents and see the consequences of going down the path as you will do with a AlphaFold kind of representation. So you can go in that direction. And for some domains, it's very clear what that is. Right, using search basically is what I'm saying, right? For general agents, TBD. what it is. But you can go in that direction. I think that's a very, very, very promising direction, yes.
This might be a bit similar to a previous question, and it might be far down the road for you guys, but have you given any thought to issues that will arise when a sizable amount or a lot of the vehicles that your AV is interacting with are other YV vehicles?
I mean, in terms of which aspect of, you mean in terms of what will happen in society, what will happen as a kind of
No,
use this
sorry, I
information, or
mean,
which
like
one?
safety-wise.
Yeah, so the problem of self-driving is that there are humans. If they weren't humans, it would be solved. So the problem is all the, and the fact that it's physical, and sometimes physical systems can break, like a wheel can break or whatever, right? But if the more self-driving systems that are out there, the easier it gets. The problem is that you cannot wait until that moment to deploy. So it's interesting that at the beginning it's harder than it's going to be at the end. But with, self-driving systems can communicate. One of the things that we need to potentially do is communication across different companies. There is infrastructure. There are companies like Capneu that are looking at, can we have a smart sensor so that we can, in advance, tell self-driving vehicles that maybe there is going to be an accident, 2 kilometers ahead. Maybe there is something, when you're at truck, changing lanes can take forever because if it's packed the highway, you're massive, right? So things like this will actually be, enhance safety, etc. But if any, this, makes things much, much, much easier. Assuming that every self-driving company does the right thing and, in a predictable manner.
Hey, thank you for the great talk. Over here.
Okay,
Sorry. I noticed that there was a lot of adverse conditions presented in terms of vision, but what about adverse conditions in terms of control? For example, in Toronto, the roads often get very slippery, tires can skid along the road. How do you deal with that in simulation? And how do you deal with that for the trucks that are actually going to be on the road here in Toronto?
Yeah, so in simulation we have a model that can simulate the perturbations. And this, these perturbations, as I mentioned before, can be because of gear shifts, can be because of wind. Actually, it turns out that we operate Dallas to Houston. There is, really, really gust of winds are a problem. You can have this because this particular material, etc. So we simulate those perturbations, and then we train the system to handle those perturbations.
I see. Great, thank you so much.
Hi, thanks for your really interesting talk. I'm curious.
Where are you?
I'm over here.
Thank you. It's like so hard to see.
I really appreciate, I think many of us here really appreciate you sharing all of these insights and these sort of unique and impactful discoveries. I'm curious if you have a business case behind publishing many of these ideas and presenting them, or if it's more from an academic standpoint.
Lovely question. Is there a business case for publishing? Absolutely not. Let's see. So I'm still, in many ways, an academic at heart sometimes, or maybe more than sometimes. So there is a few places where you can see this. One place is I like to really bring young talent to the company. We do a lot of undergrad that come, for example, to do internships where we actually give them really impactful projects, something that I haven't seen anywhere else. But I believe in talent, young talent that you can really shape. So that's one example. Publishing is another example where I believe that academia should stay relevant. And one of the reasons I joined, at the time Uber as chief scientist, 7 years ago when I went to industry, was because by staying in academia, I actually didn't know what were the important questions to ask. And I knew that everybody was using the stuff that we were doing, all the companies, right? But I couldn't get a sense oftentimes about, is this important or is this already solved? And I wanted to focus on the things that really matter. And the papers are ways to share innovation, and a lot of, we don't publish as much as before, right? We are pretty selective, but those papers are things that I think move really the field forward and that really work, right? So, you know, it puts the bar to the next level, and the hope is that this can actually shed some light for people in terms of what is important and where potentially you should be looking at if you want to do a PhD or something in this domain. Okay. The other thing that maybe is less known is we actually have a joint PhD program with U of T where you can do your PhD while being at Wabi. And that enables you to really understand and have the resources that otherwise would be impossible to really do. So I am still, you know, very, very grounded by academia, and there's a reason why I decided to be a professor, and I guess I'm still a professor. Hopefully for, hopefully for a while, but I think it's, you know, this is one way to give back.
Hi, Raquel, at the back.
Oh, there.
Yeah.
Thank you.
Well, when it comes to the model controlling the cars, the trucks, I wonder if you've had to face a trade-off between a powerful model versus a model with a smaller inference time. And if you did, then how did you handle this balance?
Yeah, so great question. So a lot of the industry, including, I guess, Waymo and others, are going for, let's try to build they're looking into what we call AV 2.0 today. And they're looking at, let's build a massive model, and hopefully that model actually will do very well, and then let's use that to distill into a smaller model. For our case, we never did that. Instead, the question that we ask is, can we build something very, very, very efficient that generalizes extremely well so that we don't need to do that? You don't need to then train with massive amount of data and spend billions of dollars in the cloud. Right? Instead is, can you build the most efficient architecture? Can you build it with really superior generalization capabilities than anybody else? And the simulator, what I then say is that every example on that simulator that you can train your system is so informative. Because when you're driving, the only thing that you really see is what was the trajectory, but you don't know anything about what is on the scene, etc., unless you use humans to, label bounding boxes and whatnot, which is very expensive. You can't do this really at a big scale. For us on the simulator, we know everything. And we can also generate, as you're learning, as you're training, the examples that are more informative. So as a consequence, the number of data points that you need is much, much, much smaller. Right. So that's what we build, which is very different.
So I think we're at time, actually, and we should stop the question and answering session here. But as a very small token of our appreciation, I have a gift.
Look at that. Thank you.
And let's thank her one more time for the talk.
All right. Oh, wait, don't go. All right, let's embarrass you a bit more.
Oh, God.
Let's thank Raquel once more for a truly, truly amazing talk. Raquel, your talk was amazing. It was truly, I really enjoyed hearing about all the incredible work that you're doing. You are really breaking new ground and making the world a much better place. We're incredibly proud of you, and we are truly honored to be able to call you one of our own. So thank you again for agreeing to do this talk. So, folks, if you enjoyed what you heard today and you want to get a bit more, I would like to encourage you to register for ARIA, our Applied Research in Action Showcase, which is happening at the Toronto Convention Center on November 14th. You'll get a chance to hear about some of the other innovations that are coming out of the Department of Computer Science, as well as some of our partner departments. So I encourage you to do that. Finally, I would like to thank everyone that was involved in the organization of this event, including folks from the Faculty of Arts and Sciences who worked really, really closely with our department's team that made this event possible, as well as everyone from Schwarz-Reitzmann who is providing support for this event. So with that in mind, I want to wish you a great evening. Keep enjoying yourself, and thank you for joining us.
Thank you for coming.